So we'll start off with Kurt Spokas. He's going to be speaking about biochar and soil and covering the growing mechanisms. Kurt is one of my favorite people, and he's here from the ARS in Minneapolis, St. Paul.
Well, I appreciate the opportunity to speak to you, as well as all of you coming here to hear my talk. I want to start today with a little story. When I was growing up, one of my favorite programs were 3-2-1 Contact that was on TV. Most of you probably don't even remember or even heard of this show before. But what it did was actually instruct people to ask why. Often in my role, I get to go to kindergarten and third grade and fifth grade classes and talk about soils. They're never afraid to ask why. And I said, that is one of our important roles as scientists, is to always ask why. So the talk of mine today is Biochar and Soil, Uncovering the Driving Mechanisms. So I'll start with a quote. There are few who realize the value of charcoal applied to soil. When you look at that, I often ask you to think about, well, who would have said that? How long ago was this published? Was this something from Eric Knight or David Yarrow at the start of the whole biochar push? Was this something in a technical document from the NRCS or the USDA highlighting the value of charcoal? Unfortunately, dates all the way back to the 1860s with J.H. Walden in his book Soil Culture. It's one of the first agronomy handbooks talking about the impact of soil on different crops. Within this book, he summarized that there are few people that know the value of charcoal being added to soil. Back in the 1790s to 1850s, charcoal was applied to soils in every way means possible, trying to improve yields in fields. So if we look back at their results in the 1800s, we see the first evidence of occasional yield improvements. This dates all the way back to the 1770s. The fascinating part to me is this is before a lot of statistics. So the actual yields in the field were validated by the neighbor. I think that's probably just as valid as a t-test these days. So there also is documentation of increased soil temperatures with earlier crop germination and emergence. This goes all the way back to the 1730s. Charcoal mixed with manures improved fertilizer action was noted in 1834. It was used for deodorizing animal manures for fertilizers in the 1873s. It also was seen to reduce pathogens, particularly for potatoes and peach trees. With one handful of charcoal with each seed as you planted it seemed to be the application rate that they promoted at the time. In fact, in 1850, there actually was a patent for an antiseptic fertilizer using peat charcoal as a primary ingredient to avoid pathogen transport. The other side of this is there's a lot of history in the material science of charcoal. This goes to some of the big names in science, from Joseph Priestley and even Benjamin Franklin, looked at the properties of each individual charcoal coming out of a kiln. They made the statement that every piece is unique, like a raindrop. I think it probably would be better for a snowflake, but they used a raindrop. But anyhow, back then they realized that even though you had the same set conditions, the variability in each piece of char was there. So, a lot of times I'm asked, well, if it was used all these times, what happened? Why aren't we currently using charcoal in agriculture? A lot of it boils down to just bad timing and bad luck. In the 1800s, we saw that the benefit of charcoal did not outweigh the cost of time and money. So you have to remember a lot of this was done individually at each individual farm. It took a lot of time for them to make charcoal and to apply it. It wasn't so much the economics. So then, as you heard this morning in layman's talk, about 1790, we discovered phosphorus. A rudimentary soil test started coming out for phosphorus and potassium. This led to actual physical guidelines for how much fertilizers of these natural products needed to be added to the soil. Charcoal was left out in the dust, so to speak, because they didn't have any soil test to say, well, how much charcoal needed to be applied to a soil. The next big boom of charcoal application in agriculture occurred in the 1900s. This was a real big time for agriculture. All the new implements were being made, new planting devices to get away from human time spent planting. In 1920, the Benton Manufacturing Company developed the planter that you see in the photo there, And it actually deposited a seed, a little bit of charcoal, and a little bit of manure as it was passed down the row. There also was a lot of interest in using coal ash as well as residual coal fines that fell through the wagons. They would scoop them up and apply to soil. Again, what happened? We had the Great Depression. This led to a lot of financial pressure. Why apply something when you can't even pay for food? Also in 1921, the first ammonia plant or synthetic fertilizer started coming on the market. It also was followed by advancement in soil testing and end fertilization recommendations. And again, it left charcoal out in the dust without actual recommendations or guidelines. So now we come to the 2000s, and what has changed is the purpose of creating charcoal. We are now creating it for climate mitigation potentials. So when I look back at all this literature, something else that strikes me as very interesting. When you look at the 1800s, their conclusions of the study was, well, it depends on the soil, the weather, and the crop. No specifics on what actually is going on, but those are the factors that influence the outcome. To me, it is fascinating. 200 years of human scientific research on charcoal. What we have done is added 2 more complications. This is again looking at the 30,000 foot level down. It depends on soil, climate, crop, but we've also added now biochar type as well as microbial interactions with the char. So this is the overall picture of what our current results of all of our experiments in charcoal have shown. The next part I want to look into is something that we are struggling with is over the permanence, and I'm not going to talk about the mechanisms of the things. What struck me in this statement was the very last line, that everything in biochar and soil can be independent of soil type and climate. To me, this was fascinating because nature is a very powerful force. It breaks down rocks. It causes degradation in minerals. How can we be so certain that we can just state that it doesn't matter on soil type and climate? So that's what really got me thinking in terms, can we just dismiss soil interactions with biochar? The problem is field aging of biochar has led to significant changes in both the chemical and physical properties after it's been exposed to soil. We have studies detailing changes in pH. It actually decreases it. Some chars mixed in some soils have observed going to acidic nature of the material. We also see CEC increases. We see the development of ionic exchange capacity, or AEC. These are things that aren't even present of properties of our original material, but put the char in soil and we develop these properties. So when this first started coming out, we started saying, well, maybe the films that are developing on the biochar are just organic films. Well, the one test I did was to see, well, what happens if we just expose that char that's been weathered to CO2? Does it absorb that atmospheric gas of CO2 directly to the char? And you can see in this little snippet of data that I'm showing is that we do have a significant increase in absorption of CO2 gas from the air onto the char. Why this is important is all of a sudden the carbon that we see in the elemental analysis around the char particle may include carbon dioxide gas from the air and not carbon from the biochar. Equally as important, the CO2 that we then measure after we collect that field exposed biochar might not represent the degradation of biochar carbon. It might solely be the degassing or degradation of this mineral coating that's on the char. So where has this left me in my entire research on char? It was about 10 years ago I started a citizen science effort. At that time I thought I would send the same biochar out to different volunteers to bury the char in their soil, send it back to me, and I could do the analysis with all my Woodbing instruments and say, look, I can calculate the degradation rate on the char. I thought this was a real good idea. I first sent it out. I didn't worry about soil type because I thought, oh, we have the NRCS soil atlas. I can pick their location, find their soil type. that would be a data point corresponding with the aging in that environment. In about 4 years after I started seeing some drastic problems. This particular example here is for an Illinois, a drummer soil series that's located in Illinois. I had a farmer that was willing to take and bury char in the split field where he had corn and soybean, and it was the same soil type across the area, and he was in continuous corn-soybean rotations. And then his neighbor across the road also said he would bury a couple bags, and I sent it to him. So we had 3 samples that were located within the same soil type. There was no drastic changes in that region. So within these mesh bags, I included some biochar. Then I put other biochar into a little Ziploc bag to eliminate any soil contact. But I still had temperature, pressure, if any changes occurred during the shipment of the char to back and forth. My initial goal in all this was I was going to weigh how much char disappeared out of the bags to get a first indication of how much char could possibly degrade. 90% of the bags that I got returned, even after we cleaned all the soil off of the outside of the particle, went through all different solvent rinses and sonications, they were left with increasing mass. What occurred was all of the soil got transported into the pores and literally got locked in where we could not dislodge it in the lab using our common methods that we usually use for rinsing soil off particles. This was a real big bummer. I almost screwed up. Here I am sitting going, oh, darn it, everything I thought I was going to do has failed. But then I started thinking, well, I have all these aged chars now. I have to do something with it because otherwise, what am I going to do with them? So then I started looking at the differences in sorption, and that's the graph that I was showing up here, where I picked glyphosate primarily because it has 3 different types of bonding. I won't bore you with all the details of that, but I just wanted some compound that had different mechanisms of different sorption properties. So on glyphosate, we have a phosphorus group, we have a nitrogen, and an organic end. So from this, I normalized all of the sorption to the ratio of the original fresh char. For the one sample that was placed in the drummer soil, we saw a decrease in sorption compared to the normal unaged biochar. The other 2 samples showed increases. Remember I said there was one sample that was in corn and soybean rotation from the farmer? Those are drummers 1 and 2. Drummer 1 was in the soybean. Drummer 2 was in corn. This difference was interesting. It has bothered me for about the last 6 years. Scratch my head, why are we having such drastic differences in sorption for the same soil, same environment, same temperature, just the difference in crops? So this got me thinking more and more about, well, what could the differences be in those soils? While I was going through the whole history and looking at charcoal application to soil, I was also looking at the whole charcoal research history. There was a lot of arguments back in the 1800s of how to save charcoal, how to preserve it, how to prevent it from aging. One of the techniques that was used back then was they put it in seawater or salt water for preservation. And I was like, gee, that sounds interesting. I wonder what it does. So I set up a little simple 2 chars, the same type, put them in a DI water, put another one in synthetic seawater. It had to keep them in between sieves, just like the water sorption tests that the standardized. This was just looking at what could the potential differences in those chars become. I was fascinated to see that with the DI water, we have sheet exfoliation after about a year being submerged in water. The synthetic sea salt one did not. As a soil physicist, I said, oh, this makes perfect sense. We have smaller pores that absorb water. They expand, causing failure of the char. In the seawater, because we have osmotic potential that prevents the water from going into those little pores, we have preservation. This is just one physical method by which char disintegrates in the environment. So because this was so fascinating to me, I started looking at a whole bunch of different salts. I did calcium, magnesium, zinc, aluminum, lithium, sodium, potassium salts, all chlorides to keep the common anion in it. I did concentrations from 0.001 molar all the way up to 1 molar. 1 molar is unrealistic unless you're in a very arid environment that has a lot of salt deposits. but the 0.01 is a typical soil solution concentration that we use. So I soak these chars for 30 days, put them on a shaker, only going one shake per 60 shakes, one shake per second or 60 shakes per minute. Then I rinse the biochar off, just put it in filter paper and taking a DI squirt bottle, squirting it off until it ran fairly clean that I didn't see any other dissolved salts coming off. I then oven dried them and then I ran various tests on them. So the first thing I looked at was pH. To my surprise, just by exposing these chars to room temperature, not high temperature, not a very aggressive diagenesis conditions, just the different salt solutions, there were salts that created an acidic biochar. All of the salts reduced the pH, but there were some that actually created an acidic biochar. Then I started looking more at water absorption, and all salt exposures above 0.01 molar increased water absorption. The thing that was the most striking was this was fairly predictable. For each salt, there was excellent correlation between the salt concentration that was exposed and then the equilibrium water content that was achieved at 99% humidity. The R-squareds for these exceeded 0.98. However, there's no clear relationship across biochar types, and I'm still scratching my head, even though I don't have too much hair left, over what the exact mechanisms are for this interaction. In addition to capacities, the kinetics are also affected in this process. And then I've looked at different absorptions of the glyphosate again. And for the zinc and iron, it had the greatest change in capacity as well as a change in the kinetics of the absorption. So I've been looking at these under SEM, TEM, Raman spectroscopy, trying to pinpoint what is going on. For the zinc chloride exposed biochar, I see that the residual zinc and chloride are still affiliated with the solid there. I go over to calcium, and I find no indication of calcium presence. The chloride is still there, but no calcium was found in the SEM world. So what I've come to realize is that the devil's in the details, or the plaque. This biochar plaque formation has been noticed with the co-composting, and it causes differing behaviors based on the dissolved salts that the char was exposed to. Other people have seen that the absorption increases stability, and it also, the addition of fertilizer changes the surface plaque on the same biochar applied to the same soil. This is what I saw when I looked at the corn and soybean difference. So my overall hypothesis right now is, could these nanoscale alterations to biochar particles in soil be the reason for the lack of historical predictability and reproducible response? So with that, just a little wrap up is saying there was no crystalline structures. The biochar attracts this amorphous cation-rich layer to the biochar surface. The part that is most confusing is it is spatially very uniform. The only people I have showed these SEM to that said they've seen something similar is the electroplating industry. That's when they say, yep, you're somehow electroplating your char particle. Still don't know the mechanisms yet. This layer is not easily removed. It is not removed by alkaline solutions, not removed by acidic. It leads to the conclusion that there is some organometal attraction. So the last point is that the carbon dioxide absorption can be simply the calcium oxide to calcium carbonate conversion. Overall, this leads me to believe that the soil solution chemistry is actually more important than the soil type and when we're making a decision on biochar applications. And thank you very much for your time.
That was a great talk. Are there any questions before I hop in? Okay, we've got Josiah.
Yeah, that was really interesting, and thank you for presenting. And I was curious about your use of the word disintegration when you were showing the deionized water versus the salt water. And I think I think that was evidence of physical decay, but I just wanted to be clear if you were implying any chemical decay.
No. This is solely a physical exfoliation process. So the chemistry of that material, if we ran it through a C&O analyzer, is statistically equal. There was no oxidation of the carbon by microbial processes.
Yeah, for a lot of the durability concerns that that would come up.
Yeah, that is a huge problem right now.
Perfect. Thank you so much.
Yep.
Could that exfoliation have been due to freeze-thaw cycles? Was the soil exposed to freezing and thawing, water getting between there expanding during freezing?
As much as I'd like to say the temperature in my lab is controlled, we do get very cold in the lab, but it was not freeze-thaw.
Are there other questions? Yeah, I do have a question. All right. You?
So you make a biochar. How do you characterize that raw biochar before you start plunging it into this sort of pathway of changes? What are the metrics you're capturing, and what more would you like to know?
There is so much more I'd like to know. The biggest problem I've been faced with in all this is what tests to actually run. I've been looking at a lot of the high-tech tools because I'm co-housed at the University of Minnesota. They have a great surface characterization lab with all these multi-million-dollar instruments to characterize surfaces. Then I take a step back and I realize it's going to be the same as Benjamin Franklin and Priestley found. Each piece of char is going to have unique signatures. How do I come up with a composite? What is an average? How many samples do I need to run to come up with that? Unfortunately, I do not have those answers yet. I'm still in the shotgun approach of throwing things at it and seeing what I come up with that sticks.
Okay, I have a question. So 2 questions, actually. So what's the mechanism for CO2 absorption, and do you know how much CO2 it'll absorb?
So we've been running capacity and absorption limits on this, and so far we haven't characterized a limit. So there's multiple factors that go into this. One is when we were exposing it to the 14C CO2, we use water and acidified little carbonate. So it's a high humidity environment. In that environment, you get layering of water molecules that absorbs the CO2. In addition, water molecules plate on that. So you get a cascading layering of water and CO2 molecules. In addition, we have the oxides that do form the carbonates. I don't think it's interaction with the actual biochar carbon. It's more this interaction with this layering that's on the char particle.
Do you think you would observe that in soils?
Yes.
So would that explain the observation that there's a decrease in net mineralization in soils from microbial priming?
It's possible.
Well, where you would expect microbial.
Yep, I think I'll use Katie's expression. It depends.
Yeah.
It depends on the capacity of the absorption of that char. The fascinating part to me is so far I've not found a predictable model for this plaque formation. I can expose it to the same conditions, and there's differences between them. So I don't know yet how we're going to get to forecasting of that.
Awesome. I'll ask you my other questions later because I think we need to switch speakers. But thank you so much for your talk.
Biochar.org appreciates the support of our sponsors, exhibitors, presenters, and attendees. We look forward to seeing you at our next conference in September 2025.